So a quick rundown on the rest of the week. Again, you have 2 sections that are due tomorrow, section 6.1 and 6.2. All that's due on Saturday is that review for exam 3. That's it. And on Sunday is exam 3. It covers all of chapter 5 and the first 2 sections of 6.1 and 6.2. You can go ahead and schedule that with ProctorU right now. And what I decided to do is today we're going to do section 6.2. Tomorrow we'll come in and review for the exam. So I've printed out the exam off of MyLab Math, and I'll pick similar problems and talk about them. But on Thursday, because I don't want to move forward into new material until you've taken that exam, what we're going to do is just have an office hour at 9. So I will log into Zoom at 9. I'll be right here as normal. And you have to have the questions. So if you have any questions that we haven't been answering or you're confused about something, we're just going to treat that hour as an office hour. I'll log in at 9 as normal, and I'll go until whenever you guys are done with me. So 9 till whatever. But if nobody logs in, I'm assuming that you don't have any questions. So you do not have to attend. I will not take attendance that day. But that way, if you have anything that you need to get cleared up before the exam, you can ask. So that's what we're going to do this Thursday. We'll try it and see how that goes. I did look at section 6.1 in terms of the homework problems that were picked. Again, these were all picked by a committee last summer. So they didn't actually pick any of the compositions where you're composing fractions together. They did pick one where you're composing a radical with a linear function. So this is a brief comment from section yesterday. So this is section 6.1, kind of continued. I just want to make sure that we're okay. So let's do, let's let f of x be the square root of x plus 2. And we're going to let g of x be x squared minus 1. So f of x is equal to x plus 2. G of x is equal to x squared minus 1. So let's come in and find f compose g and the domain. And we'll only do one of them. So we learned yesterday that this means what we're really doing is finding f of x squared minus 1. So that means we're going to take all of this function g and plug it in for that x. So that would give me the square root of x squared minus 1 and then plus 2. Not a lot of cleanup here. So that's just going to give me x squared plus 1. So, okay, but now we got to figure out what its domain is. So the composition is not the hard part, it's the domain. So let's walk through our steps again from yesterday. So step 1 is to find the domain of the input. And in this problem, the input is the g of x. So when I look at g of x, what is its domain? Does g of x have any restrictions on it? Does it have any radicals or square roots in the denominator?
No.
No. So its domain is all real numbers. So it does not add any restrictions to our answer. So step 2. We're going to come and take a look at our output, which was the square root of x squared plus 1. This is where things get fun. So what we need to do is find the domain of this. So we're asking what numbers can we plug into here where this blows up or has issues. So from what we did in just chapter 5, you would take the inside, that's the x squared plus 1, set it greater than or equal to 0, and then solve it. So let's think about this from what we do know. We know that this is a parabola. We know that this particular parabola has been shifted up 1, so the graph would look something like this. So is this parabola ever negative? Does it ever fall below the x-axis? Well, no, it's always above. So this is always true. So our domain here is also going to be from negative infinity to infinity. So it doesn't have any restrictions because that parabola is never below the x-axis. Well, that makes it easy. So then in step 3, the domain of the function would be a combination of these two. So we can simply say that our domain is going to go from negative infinity to infinity. So there's a lot of analysis that has to go on to figure out these domains. So step 3, negative infinity to infinity. So it's kind of similar to the one that you're going to have. I think it's a little more complicated, but it's similar. But no fractions, no composing fractions. Darn it all, it's a good problem. Okay, let's move into section 6.2. I did email out some notes yesterday afternoon. Hopefully you got them and took a look at them. If not, you can. So section 6.2 has a lot of stuff in it, but it's luckily stuff that you've mostly seen before. So section 6.2 is on one-to-one, and then also inverse functions. So one-to-one and inverse functions. Okay, so what we've been doing in the class is we basically have been taking all of our equations that we dealt with in the first two chapters, chapter 1 and 2, and we can classify them as either a function or not a function. And we know that a function passes a vertical line test. So VLT for vertical line test. So we did that in chapter 3. We laid the groundwork for what a function was. Well, today what we're going to do is we're going to take this classification of functions and we're going to classify them even further into something that's called a one-to-one or not. One-to-one. So it's either going to be a one-to-one function or not one-to-one. And what we're really after is this side of the classification system, because we need to move forward using this side, not this side. So just so you know why we're doing it is because we need this one-to-one-ness in order to move on to the next section. Okay. So what the heck is one-to-one and what does it mean? So there's a technical definition on the handout. It's kind of mathematical. So it says a function is one-to-one if, so if f of x1 equals f of x2 when or then x1 equals x2. Okay, well that's interesting, but what the heck does that tell me? More importantly, what it really means is that it means also f of x1 does not equal f of x2 when x1 does not equal x2. So that's the math part of this. Okay, that really doesn't help us too much. What this means is that each input gives a single output. Okay, well that's the definition of a function. But what we're going to add on here is really important. And each output comes from a single input. And that's what this second part is adding on to it. So not only does one input give one output, each output can only come from one input. And that's why it's called one-to-one. One input, one output, one output, one input. Okay, so this is what it means. This is the technical definition. What the heck does it look like? So we're going to come in and draw two of our favorite functions, or functions that we've dealt a lot with. So in other words, we're going to draw our friend the parabola. F of x is equal to x squared. We know it's a function because it passes the vertical line test. And then we're also going to graph f of x equals x cubed, our cubic function, that S shape that we've seen. Okay. So my question is whether or not that parabola is a one-to-one function. Well, no, it's not, because if I pick a single y value right here and follow it over, doesn't it have two different x values that it comes from? So it's got an x value on this side and an x value on this side. So that parabola is not one-to-one, because one output came from two different inputs. What about the S shape? Well, every single y value we pick on it has a single x value that is coming from. So this is one-to-one. So dealing with two functions that we've already looked at, we can see one is one-to-one and one is not one-to-one. So what this translates into is a horizontal line test, which works nice for us because we know the vertical line test. So we're going to talk about this in terms of a horizontal line test. So in other words, if you can pass a horizontal line along its length and it intersects more than once anywhere, it's not one-to-one. If you can pass it along its length and it only intersects one time, then it is one-to-one. So that gives us a clear test for a one-to-one function. Okay, any questions about a function being one-to-one? Now, not all of them that we've graphed are one-to-one, right? So some rational functions are, like the reciprocal function would be, but other rational functions are not. So there's a wide variety out there. So now that we know what one-to-one means, we can move on to the idea of an inverse. So if a function is one-to-one, then it has an inverse. So if a function is one-to-one, then it has something called an inverse. Okay, so I'm going to pause right there, and I'm kind of through the front page of my handout. What the heck is an inverse function? So I'm going to go way back to like when you were 2 and you learned to dress yourself. So in the morning, when you dressed yourself to go outside on a cold day, you would put your sock on and then you would put your shoe on. And so that was getting dressed. So at the end of the day, when you come in and go to bed kind of thing, what you have to do first is take your shoe off and then your sock off. So putting the sock on and shoe on is one direction. Taking them off, you have to do it in the opposite direction or the inverse function. So you've been doing inverse functions all your life. We just never called them inverse functions. So we skip forward to grade school. In grade school, in first grade, you learned after counting how to add numbers together. So what undoes addition?
Subtraction.
Beautiful. So addition and subtraction are inverse functions because they undo each other. Go forward into what, 4th or 5th grade, you learn to multiply, and what's the inverse of multiplication?
Divide.
Yep, division. That's exactly it. And then we can continue this forward into squares and square roots, cube roots and cubes. So the inverse of division is multiplication. So we've got lots of different things out there that let us undo each other. So, okay. So there's a technical definition. It says that an inverse function for f is one that takes the results of the elements of the range and returns the original elements of the domain. So that's a little awkward. Actually, it's a lot awkward if you ask me. So it simply says that you're switching the domain and the range. So we're going to consider the function f of x equals 2x minus 3. Now we know that that's a line. And if we think about that line, just as a side note, it's got a y-intercept down here at -3. It's got a slope of up 2 over 1, up 2 over 1. And we can see that this is 1, 2, 1. It passes that horizontal line test. So because it's 1-to-1, it has an inverse function. Okay. So what you then see on the handout is this picture, and it starts off with an x. So in other words, if I input x into this function, what you're going to do is multiply by 2. So we can see that the first thing you do is multiply by 2. Looks like too many x's, so we're going to say times 2. So that would give me my 2x. And then what you do is you would be to subtract 3. So then you subtract 3 and you'd get 2x minus 3. And you'd get your output. So here's your input. This is what you would get as your output, and you'd call that y. Okay, well, if you come in and do the opposite of this in the opposite order, then that means that the inverse function is going to come in, and first of all, the opposite of subtracting 3 would be to add 3. And then you'd come in and instead of multiplying by 2, you'd have to divide by 2. So we'd say divide by 2. And that would get me back to the original. So if I input an x value, let's go ahead and input an x value. So let's let x equal 5. So 5 times 2 is 10. And then we're going to take 10 minus 3, and we output a 7. If I take that 7 and do the inverse operation, 7 plus 3 gives me 10, and 10 divided by 2 gives me 5. So do you see it gave me back the original one? So this again, you start off with a naked foot at the beginning of the day. At the end of the day, you have a naked foot again. So that's what the inverse function does. So the original function is what we call f of x. The notation for an inverse function is, and this looks a little strange to us, you're going to write the f for function, and then you're going to put a -1 up there as an exponent, but it doesn't mean a negative exponent. It means the inverse. So this is the notation that tells everybody in the math world that you're talking about the inverse function. So we could do the inverse function for the one we just found. So we would have f inverse of x. So the first thing you're going to do is take x and add 3 to it. And that's what we did. We took our input value, we added 3 to it. Then we divided by 2. So that would put it over 2. So without even knowing how to go about doing it, we can find that inverse function. So by just undoing the original function in the opposite order. It goes on to tell you that if f is a 1-to-1, then it has an inverse with ordered pairs a and b. Let's write that down, actually. That's kind of important. I'm going to keep using this example. So in other words, in the original function, when we put in a 5, we got out a 7. So we put in the 5, multiplied it by 2, and subtracted the 3, we got a 7. Then on the inverse function, when we put in the 7, we got back the 5. So we put in the 7 as our input, and the result was a 5. So do you see that the x's and y values have been flipped? So that means that whatever you have as the domain on this end becomes the range over here. So the set of x values here becomes the set of y values on the inverse, and the set of y values on the original function becomes the set of x values on the inverse. I know it feels like I'm just talking, because we have to lay that groundwork more than anything else. And it does go on to say that in step 2. It says the range of f will be the domain of the inverse. The domain of f will be the range of the inverse. It then gives you a caution about what this means. Again, that does not mean a negative exponent, so no putting anything into the denominators. Okay. Again, all we're doing today is laying groundwork for section 6.3 and 6.4. So you're going to say, why do I need this? And I can't tell you that until next week. So, example 2 on my handout asks us to find the inverse of each function. The first function is just a set of points. So we have the point -2, -7. I also have the point -1, 0. I have the point 0, 1. I have the point 1, 2, and the point 2, 9. So that's the original function. So we're going to call that f of x. Okay, so in order to find the inverse function, all we have to do is take every single x value and make it into a y value, and take all the y values and make them into x values. So for the inverse function, the first point would be -7, -2. Notice I'm not touching the signs. All I'm doing is taking the x and y and flipping them. So then the next point would be 0, -1. The next point would be 1, 0. The next point would be 2, 1. And the last point would be 9, 2. So all we did is we took our domain and switched it to the range of the inverse. We took the range of the original and made it the domain of the inverse. So you're just switching the x and y values. Okay, part B on that same problem says, okay, what about f of x is equal to 1/4 x minus 3. Now, in a minute, I'm going to give you specific directions on how to find the inverse, but let's see, because this is a line again, if we can do it without having to do it in terms of the algebra. Let's see if we can talk ourselves through it. So if you had an input value into this function, if you had a specific x value, the very first thing you would be doing would be to divide by 4. So the first step would be to divide by 4. And then once you had that, you'd subtract 3. So then you're going to subtract 3. So if I want to find the inverse function, I have to do it in the opposite order. Again, shoes and socks. So the very first thing we're going to do is take our input, which is x, and we're going to add 3. So the first thing we have to do is undo this subtracting 3 by adding 3, which is what we did. And then we're going to undo the division by 4 by multiplying by 4. So I'm going to put the entire thing in parentheses and put in a 4. So I have 4 times the quantity x plus 3. Okay, let's go check it and see if that works, if that's actually what's going to happen. So check. So what we're going to do is we're going to put in a value into the original function. So what I'm going to do is pick an x value and see what we get as the output. And let's take something that's divisible by 4. So let's use 8. Okay, so 8 divided by 4 is 2. 2 minus 3 is a negative 1. Now, if we've done it correctly, if we plug in that negative 1 into our function and then divide or do what it says, we should get the right answer. Okay, so we're going to take negative 1 plus 3. That would give me 2. And 2 times 4 is 8. So sure enough, it checks because we can see the x and y values flipping. So, okay, so this idea of looking at it from this point of view works really well when they're lines. But if the function gets a little more complicated, then the whole process gets a little more complicated. So let's go do one that's uglier. Any comments or questions so far?
No.
Okay.
We're on a roll. I don't know if you can tell, but I went and cleaned my erasers yesterday and it's erasing much better. Example 3 says, let's state the domain and range of f of x equals 2 over x plus 3. Then we're going to use the algebraic method to find the inverse function and then state its domain and range also. So I'm not going to necessarily do that in this order, but what you then see is a little chart. I love this little chart just because it organizes everything for me. And we're going to do domain and range. Okie dokie. So this goes back to chapter what, 4? No, chapter 5, when we graphed rational functions. So what number can you not use in the domain of this, what number can you not use in the denominator of this function?
Negative 3.
Yep. So we're going to say negative infinity to negative 3 and negative 3 to infinity. Beautiful. So that is easy. We know that. Okay, the range is going to come from the horizontal asymptote. So again, what we're saying is the vertical asymptote is at x equal negative 3. The horizontal asymptote, if you remember, comes from the degree of the numerator and the degree of the denominator. That's just last week. We know that this one is bottom heavy, and anytime it's bottom heavy, it goes to the x-axis. So its horizontal asymptote would be y equal to 0. So my range, without graphing it, is going to go from negative infinity to 0 and 0 to infinity. You see how slick that was to tie into last week and also the stuff that's on the exam coming up. So, okay, so we did that. Now we're going to go find the inverse. So the second part of it is to find f inverse. So we're going to write out some steps to use the algebraic method. Notice it's not as easy this time. Your input's a lot uglier in terms of words to describe it, so we'll use the algebraic method. So the very first thing you're going to do is replace f of x with y. And that's because we just think better in terms of y. You're used to solving in terms of y. So we're going to rewrite this as y equals 2 over x plus 3. Our next step is going to be to come in and switch x and y. Okay, what? So that means any place there's an x, I'm going to write a y, and any place there's a y, I'm going to write an x. So I've simply swapped my variables. This is the actual inversing. This is taking the domain and making it the range, and taking the range and making it the domain. So you're swapping the x's and the y's. Step 3, we're going to solve for y. So I'm going to come in and solve everything for y. So to do that, I'm going to have to clear the fraction. So I'm going to multiply both sides by y plus 3. So I'll have on this side x times y plus 3. On the other side, the y plus 3 is going to cancel, and I just have my 2. Now you can do this a couple of different ways at this point. Because we're solving for y, you could divide the x out of there, and that will work. I tend to distribute because it sets us up for later work. So I'm going to call this xy plus 3x equals 2. Then I'll move this 3x. Again, we're solving for y. It's right here. I'm going to move that 3x over. So xy equals 2 minus 3x. And then I'll divide the x out of there. So it's the same answer in a slightly different fashion. So y equals 2 minus 3x all over x. So again, I distributed the x in, then I subtracted the 3x, and then we divided by x. So we've isolated our y. So then step 4, we're going to replace y with f inverse. So now we'll write the correct notation. So our inverse function is going to be 2 minus 3x over x. And there's the inverse. So that was the algebraic method for the inverse. Okay, great, wonderful, woohoo! Now, if we've done everything correctly, our domain and range up here should swap. So we're going to let this work for us. So we can see that in the denominator of this function, I cannot use 0. So that tells me the domain is from negative infinity to 0 and from 0 to infinity. So we can see that from the function itself. To get the range, I need the horizontal asymptote. The horizontal asymptote comes from the degrees. This time the degrees are equal. I have an x in the numerator and an x in the denominator. So then the horizontal asymptote becomes the ratio of the coefficients. That would be negative 3 over 1, which is a negative 3. So we can't use negative 3. So negative infinity to negative 3 and negative 3 to infinity. Whoops. And there it is. And sure enough, you should be able to see how that domain and range have switched. So the domain is down here as the range, and this range is up here as the domain. And that will always happen for inverse functions. So nice. And that's about as ugly as they're going to get for you guys. They don't get really, really ugly. When you head into pre-calc, they might get a little uglier, not too much. So, let's see the next example. Is everybody okay with that? And again, you did these in 101. They just weren't quite this ugly. So in fact, that seems to be a common theme. You do it at a basic level in the first class, and then it gets a little uglier in the next class. So it says in cases where a given function is not one-to-one, we can sometimes restrict the domain to create a function that is, and then determine the inverse function. So I'm looking at example 4. F of x is equal to the quantity x plus 1 squared. So I want to restrict the domain to create the one-to-one, then find the inverse, and then do and then find the domain and range of both. Okay, so let's think about what this is. First of all, we know that this is a parabola because it's an x squared. We know that it's been shifted, what, left 1? So pulling our transformation work back in. So this particular parabola looks like that. Right now, it's not one-to-one. But what we can do is say, well, let's, instead of you looking at both halves of the parabola, let's just look at one half of the parabola. So what I'm going to do is I'm going to restrict the domain to 0. I'm sorry, not 0, negative 1 to infinity. Okay, negative 1 to infinity. And what that's going to do is that's going to take off the left side of that picture, and now it's 1-to-1. So now the function is 1-to-1. So we can restrict the domain in order to make it 1-to-1. Part of that's because in our class we don't have enough functions that are 1-to-1, so we pull this into it. Okay, so what we know right now, f of x, f inverse. We know the domain of the original function is going to be 1 to infinity. And now I have to figure out the range. Okay? Well, take a look at the picture. The picture will tell me my range. I graphed it. Let that graph work for you. What's the range of that function once we restricted its domain?
0 to infinity.
Yep, that's exactly it. So now without even finding the inverse, I know I can flip these. So the domain of the inverse is going to be 0 to infinity, and the range is going to be 1 to infinity. Whoop, -1. Sorry. Don't drop my negatives. There it is. So without even knowing the inverse function, we can do that. Okay, let's go through the algebraic method and find the inverse just to get a second one into your notes. So we need to find f inverse. So again, the first step was to replace f of x with y. So y equals the quantity x plus 1 squared. So that was step 1. Step 2 is to switch the x's and the y's. That's the actual process of inversing going on. So now I have x equals the quantity 1 plus y squared. Step 3, we need to solve that for y. Well, the first thing we have to do to get y by itself is to take the square root of both sides. Now, just a brief comment, you are solving, so technically you need a plus or minus here, but if I do a plus or minus, I'm going to get 2 halves of a parabola, and I don't want that, so I'm only going to pick up the positive case. Because we kind of only picked up the right side, we're only going to pick up the right side, so we won't need that plus or minus. And then all we have to do is move the 1. That 1 is outside of that radical. So step 4 is to finally come in and say, well, f inverse of x is equal to the square root of x minus 1. So let's think about that from our transformation point of view. We know the square root function is a half a parabola, and this shows that it's been shifted down 1. So the inverse function is sitting down here and is looking like that. And there's the inverse function. So, woohoo! We can see that, yes, indeed, it has a domain from 0 to infinity, and it has a range from -1 to infinity. So, nice. Okay, any problem with that? And we expected it, because we know that to undo a square, you have to do a square root. So, okay, what I'd like to point out, because I have this picture on the board, is if I draw in the line y equal to x. So y equal to x. That's our identity function from way back in chapter 3. Y equals x. Do we notice that this thing has symmetry about that? So in other words, if I take this function and fold it, it folds onto this function, or vice versa. So it's important to note that a function and its inverse have symmetry about the line y equal to x. So even if you're just given the graph of a function, you can find its inverse graph by folding it across that line y equal to x. Okay, a couple more comments and work, and we're almost there. So you may be wondering why we needed the idea of composite, because we haven't done anything with a composite yet today, but we spent time on it yesterday. So why do we need a composite function? Well, the composite lets us verify a function and its inverse. So we need a composition to verify inverses. So the composition is the only way to verify that 2 functions are inverses. So in other words, it says on your handout that f compose f inverse is the same thing as f inverse compose f, and that's equal to x. So what this is basically saying is that if you take a function and compose it with its inverse, you will get the same answer as if you take the inverse and compose it with f, and both of those cases are going to give us x. So you're saying, okie dokie. So I'm going to go back. Oh, no, example 5, I can't go back. So example 5 says, is use the algebraic method to find the inverse and then verify it's correct. So f of x is equal to 2x minus 2/3 x minus 5. So there's a function. That's a line again. So it's got a positive slope and a negative y-intercept. It's definitely 1 to 1. So let's come in and find the inverse. Y equals 2/3 x minus 5. We'll switch our x's and y's. This is step 2. So x equals 2/3 y minus 5. And now we'll solve for y. So we're going to add the 5 over. And in this case, I'm going to have to multiply both sides by 3/2 to clear the fraction. So y equals 3/2 times x plus 5. You could distribute it in, but it doesn't distribute nicely, so I'm not going to distribute it in. So we found our inverse. Our inverse is 3/2 times x plus 5. And this should make sense, right? The input here, you would multiply by 2/3 and then subtract 5. So in the opposite order, you would have to add the 5 and then multiply by the reciprocal. So, okay, so that's the first part. Finding the inverse should be second nature. You've done that before. But now what we want to do is to verify. And this is important, especially if you're moving on into Math 124 or 126. We're going to verify. So what we're going to do is come in and find F compose, F inverse. It's good practice for yesterday's homework. So that means I'm going to pick up this entire function and I'm going to plug it right there. Okay. So that's 2/3. And then in place of that x, I'm going to write 3/2 times x plus 5. And then outside of that is minus 5. So again, the parentheses there just so we can see that I'm replacing that x. So that entire function is replacing that x. Okay, let's clean that up. Well, what's going to happen to the 2/3 and the 3/2? Well, they're going to cancel. That's going to give me x plus 5 minus 5, which sure enough is x. And that's what they said. If I take F compose F inverse, I should get x. This is simply saying that if you put an input, you get an output. If you take that output and put it into the inverse, you'll get back to the input. So that's all this is saying. Let's do the other one. You have to do both. So now we're going to take F inverse and compose it with F. So now we're doing the replacement in the opposite direction. So we're going to take all of this and plug it in for that x right there. So that'll give us 3/2. And in parentheses, in place of that x, I'm going to use the 2/3 x minus 5, and then I'll have plus 5, and then I'll close my parentheses. So again, all we're doing is replacing that x with the other function. Okay, well, this time what happens is those 5s are going to cancel first. And then we'll see that the 2/3 and the 3/2 are going to cancel and give me just x. So notice again, they're canceling in the opposite orders. When we did it this way, the 2/3 and 3/2 canceled, then the 5s canceled. Here, the 5s cancel, and then the 3/2 and the 2/3. So we verified it, we are good to go. Nice. I don't know why I really like this stuff. I think it's because it leads into that exponential functions so nicely. So, comments or questions about verifying? With the online homework, it's a little hard to do it, but it's hard to make sure you're doing it this way when they're just looking for the answer. Okay, so example 6 just ties back to something we already talked about. It says for each graph shown below, draw a graph of the inverse function. So for part A, the original graph has a point down here at 0, -2, and another point over here at 2, 0. And it looks like this. So this is 0, -2, this is 2, 0, this is the original function. So if I want to graph its inverse, all I have to do is take those coordinates and reverse them. So 0, -2 is going to come over here as -2, 0. 2, 0 would come up here as 0, 2. And I know it should have the same shape, so it's going to look something like that. So there's the graph of the inverse. Without even knowing the function, I know what its inverse graph looks like. I'm going to point out again that that line y equal to x is sitting right there. And I don't know that you can see that. Let me try that again. It's sitting right there. And again, notice that this time the function and its inverse are crossing, and they cross along that line, which is always true. So again, you must fold across that line. We can see that folding going on. Okay, and then the last example has a function that's a little uglier. So part B on that one. Okay, so I have a point that's over here at -5, -2. That's -5, -2. I'm going to call it the origin just because it makes it easier. And then we have another point over there at 2, 4. 2, 2, 4. So it's got a curve that's coming in through this. And then, let's see, this side's got a point at 6, 6, 5. So 6, 5. And on the other side, I think it's 8, -8. So 5, 6, 7, 8. That point is -8, -8. Okay, there's the original function. Whew. Sorry, that took longer than it should have. Okay, well, we know it's 1-to-1 because it passes that horizontal line test. Okay, so now we're going to come in and find the inverse function. All we have to do is take every pair of points and switch the x's and y's. So the point that's -8, -8 is still at -8, -8. That's not going to change. The point that's at -5, -2 is going to become -2, -5, which is going to be right here. So again, that is now -2, -5. The origin is going to be the origin. Nothing's going to change there. The point that was 2, 4 is now 4, 2. So, okay, we know it's straight through here. It then does a curve, and then the point 5, 6 is going to be up here. 5, 6. And there's our inverse function. So, woohoo! A lot harder to see it, but sure enough, they still reflect over that line, x = y, still flipping back and forth across this line. It's okay for the function and its inverse to cross. So where we're headed with this next week is we're going to introduce the exponential function. It's a 1-to-1 function. So we know it has to have an inverse, which we will do on Tuesday as the logarithmic function. So that's why we need this to be able to move forward. So, okay, and then it should be downhill after this. So these are the last rough 2 sections. Everything should be downhill. So, okay, any comments or questions about 1-to-1 or inverse functions?
None.
No, are you awake? Okay. Have a great day. Enjoy it. And we'll talk about the exam and review for the exam tomorrow, okay?
Okay.
Sounds good.
Bye-bye.
Bye.
Bye.